We're going to take a look at the concept of pressure, specifically fluid pressure, but first we're going to take a minute to define pressure itself. And then we're going to talk about pressure as a function of depth of the fluid. So, why is it that when you go down, swim down to the bottom of like a 10-foot pool, you feel your ears like almost pop or even get a little bit heavy? What's happening? Yeah. You feel the pressure from what? Water above you. So water above you that's creating pressure. Now, right now, guys, I don't know if you know it, but there's a ton of pressure on you. There's a lot of pressure on you. It's called atmospheric pressure. The atmosphere above you weighs, listen, the atmosphere above you weighs a lot. When you dive underwater and you go down like 10 feet, all you're feeling is, maybe, I don't know, like a few psi of pressure. Right now, you are feeling 14.7 psi of pressure. You just don't know it because humans and animals have adapted to live on the Earth's surface. So the pressure of the atmosphere above us, we are not normalized, we are used to. If you go to another planet where the atmosphere is different, the pressure completely could mess up your body. The human body is made or has evolved over time to adapt to the pressure that is felt by the atmosphere above it. It is 14.7 psi. That's what 1 atmosphere is defined as. In other units, it's called 101 kilopascals. Pascal is the unit of pressure we see today. So every day when you walk around, you're feeling a lot of pressure. 14.7 psi. But your body is used to it, so it's like there's no pressure really. So atmospheric pressure sometimes is kind of neglected because everything that exists is used to that pressure. But the minute you look at structures underwater, underground, you have to consider that pressure. Because structures themselves aren't biological, beings and are adapted to that atmospheric pressure. So over time, we as humans have become adjusted to this pressure. So we don't really think of it. So when we dive down in the water, we might feel 1 or 2 psi from the water. But really we're feeling 15.7 psi. It's the atmosphere plus the water on top of us. We're feeling it. Okay, so there's a lot of applications of this topic today with pressure. We're going to see how it also relates to flow rate in the next section. So let's first start with the definition of pressure. Anybody, I usually would say ladies, but maybe some gentlemen, anybody ever was a dancer when they were younger, maybe ballerina or any type of dancing in general? Okay.
Come on, Jack.
So it's usually some of the ladies, but maybe some guys take dancing classes. So, listen. Anybody have those that raised their hand were ballerina when they were younger? Okay. When you were ballet, wasn't it very difficult to stand on your tippy toes? When you were a little girl and you tried doing that, or even a boy, all the girls raised their hand here? So, the reason it was really difficult, what were you doing when you were standing? It's easy to demonstrate, just literally standing like that. Why is it more difficult to stand on your toes than to stand flat-footed? It's very easy to stand flat-footed, but when I do this, it makes it more difficult. I have to strain, I feel my muscles pulling on them. Dirks, why?
The more force put on a smaller area, the pressure.
Yeah, the force you're putting down is the same. The force downward is my weight. If I stand like this, half my weight is on one foot, half is on the other. If I start lifting up onto my tippy toes, now the contact area on the ground is much smaller. Look at our definition of pressure. It's inversely related to contact area. So as a result, if I stand on my tippy toes, I'm reducing the contact area, which, as Dirks mentioned, increases the pressure. Increases the pressure. How many people have gotten acupuncture before? Anybody got acupuncture? Okay. Now, the needles are so thin that you're not really noticing them when you get acupuncture, right? Has anyone ever seen examples where somebody would lay on nail beds, though? Ever seen that before? Not torture. Better nail beds. Thank you. Better nails. Why do they not get like holes in their back? Why are they not cut by it? What are they doing?
You're distributing your weight across all the little needles.
Exactly right. You're taking the force and you're distributing it amongst each of those different pinpoints. So really what you're doing is you're increasing the contact area. And that's physically what you're really doing there. Who else can think of an example? What's an example of changing contact area to change pressure.
When you're going across like a frozen lake or something, you're supposed to lay flat because instead of walk, because we're distributing your entire weight across the whole area.
Yeah, when you're providing water and you want to keep yourself afloat, usually you would lay on your back so there's more contact area there. There's more contact area, the less pressure needed to keep you up, so it's easier to stay afloat. Also having to do with buoyancy. What else?
This is a question for the before, but do you babies in their mother's stomach feel the pressure already? Or do they only
So-
when they come out?
We're going to learn today about something called Pascal's principle. And Pascal's principle states that in a closed system, which is what the baby is in the uterus, in a closed system, in the embryonic sac, is that the right word? The pressure is a constant value of it. I don't know what that pressure is to be 100% sure, but it's not changing. It's a fixed value. So when babies are born inside of when they're still growing and stuff, the pressure in there remains the same throughout the whole time.
But then when they come out, do they feel the different pressure inside and
It probably is a differential in pressure. Yeah, it probably is. No, I don't know. It's a really good question, Cooper. Do the babies have a difference or feel the difference in pressure of the atmosphere when they come out? I don't know. That's a really good question. I know that inside of the embryonic sac is definitely a fixed pressure. But whether it's a differential when they're being born or not, I don't know. It's a really good question. Maybe I can research it or maybe look it up for us.
When they just feel it, they don't feel it separately, they just feel it because of the
Gradual as they're birthing, yeah. I don't know. I really don't know. It's a really good question. Our units of pressure are pascals. We're going to talk about a scientist. His last name was Pascal. We're going to talk about Pascal's principle. And Pascal's, the units are named after him. And they're represented by Newton per square meter. Okay, Newton per square meter. Any questions on this? Pretty easy, right? The idea of this? Let's see. All right, let's take a look at pressure specifically now. This is what I was talking about. Why did I put a picture of somebody hunched over?
does the pressure be
Yeah, like it's a joke of it, but like think about pressure on you, right? You're always having pressure on you. There's always pressure on you because of atmospheric pressure. Okay, so we define atmospheric pressure as 1 times 10 to the 5th pascals. Some books will write it this way. Some will write it as 101.3 kilopascals. Kilo means 10 to the 3rd, and I have another 2 spots, so that's where the 10 to the 5th comes from here. Okay, but depending on the book you use, it can be written either way. 101.3 kilopascals, or some will write it as 1 times 10 to the 5th
We always
pascals.
want to keep it in pascals, though, right?
Yeah, the standard unit we're going to use is pascals because that's a metric unit. Now, in the US, we use PSI. 14.7 PSI is atmospheric pressure. That's what the equivalent of 101.3 kilopascals is. 14.7 PSI. Before PSI was invented, there was a unit called TOR. T-O-R-R-E? I think it's T-O-R-R, actually. But it's not used anymore. Okay? Same unit as PSI. TOR is 1 PSI. Another unit of pressure for a long time that was used was millimeters of mercury. And it had to do with what's called a hydraulic press, where there was mercury in a chamber, and the mercury would flow based on how much pressure it felt. If the mercury flowed up, there'd be a higher amount of millimeters of mercury. It was a measurement of like a graduated cylinder. But now we use PSI in the US and pascals in every other country. Okay? Those are the standard units we're going to be looking at here. Let's take a look at Pascal's principle. So, Pascal's principle tells us that in a closed system, if there's pressure applied to a fluid, it's transmitted equally to every point of the fluid and to the walls in that container. So for example, you pump up your tire in your car, right? You connect it to your air pump. What if there's like a... Does anyone have a pump in their car? You hook it into like the... What is that called? It's not the cigarette lighter anymore. What do you call it now?
That's what
They don't have cigarette
the
lighters.
charger
It's not.
so.
The charger port, whatever. You hook it up to your charger port in your car. There's a little pump, a little compressor. It compresses air, pushes the air into your tire to pump up your tire. Or you go to the gas station, right? You don't use a hand pump for your car. You use a hand pump for your bike. So when you're pumping up the pressure in your tire, every single location in the actual tire feels the same pressure. It's transmitted equally. So the pressure on one wall of the tire, or one location, is the same as another. So the minute you have a little cut in your tire, the pressure of that location is going to be the same as all the others, but since there's a structural instability, it can tear on that location. But the concept is that the pressure is transmitted equally. Now, here's your second bonus opportunity. Go home and do the egg experiment, but in your hand. Take an egg, put it the long way across your hand. So, if this apple were the egg right here, okay, imagine the egg was standing up like this. So it's taller than it is wider. Okay, so it's a tall egg like this, here's the width of it, here's the egg itself. Take it, rotate it, so that it's longer this way. Put it in your hand. Okay, now when it's in your hand, it's not going to be that large. But take it, put it in your hand. Now, what you need to do is difficult. You need to get your whole hand around it. If you have your hand around the egg like this, and you squeeze it like this, it's going to crack. I 100% guarantee you it will crack. If you hold the egg like this, it will crack. You need to literally, and this is tough because I can't even get my hand around it. Let's say this is the end, it'll be easier. Okay? You need to get your hand around it like this. Completely around the egg, and squeeze as hard as you can. But try to squeeze equally. So see how I'm squeezing up here with my thumb, here with my fingers, here with my palm. I'm trying to distribute the pressure evenly by squeezing. If I did this, it's going to break. If I did this, it's going to break. Squeeze it like this, it's going to break. Try and get the whole egg in your hand and try and squeeze it equally from all sides. It won't break. It's kind of crazy to think about it. The reason being, you apply pressure to the egg, the fluid inside applies pressure back equally to the walls. But it's only if you apply a distributed pressure to the egg. If you don't, it will break in your hand.
All we do is just fill it.
Okay? You can see it, so all you need to do is record. So record yourself doing it. Show me like that you're actually physically doing it. You'll see, I can see your arm tensing. I'll see you squeezing. But really, squeeze it hard. See it yourself, and you'll notice it right away. You want to crack it again, you crack it again, I don't care. But just put pressure on the egg, evenly distributed. You don't need to make a big thing out of it. Like last year. What's that? Sure. But I would use different eggs. Don't use the same egg. Okay? The egg shell could alter due to the salt a little bit. The actual shell itself is sort of thin, so you might actually break it if it's the egg that's out of the water. Okay? Alright, let's look at the example of an application of Pascal. So, Pascal's principle tells us again that if there's a pressure applied to a fluid in a closed system, the pressure is equally distributed. So as a result, a simple application is called a hydraulic lift. A piston is very similar to this. A piston uses the same concept. You apply a force on one side, and it raises the fluid level on the other side. So look at this example here. You apply a force on the right-hand side, apply a force over here on the right-hand side. As a result, the force that you apply on the right-hand side is then distributed over here with a different value. And we'll figure that out mathematically in a second, how that works. But you apply a force, the force is magnified, that force can then lift a very, very heavy object. You do not have to apply a large force. This F1 is much less than F2. Now, reasoning behind that. Pascal's principle tells us pressure throughout is equal. So let's call this location 1 and call this location 2. And if pressure throughout a closed system is equal, we could say that the pressure here at location 1 is the same as the pressure at location 2. So write that first. It's a capital P. These are capital P's for pressure. Now, if that is true, the definition of pressure from the beginning can be substituted. Pressure was defined as?
1 times 10 to the fifth.
That's atmospheric pressure, and that's the value. The definition of pressure is? Force over area. F1 over A1, whoops, equals, oh, why am I writing 2? I'm jumping ahead of myself. F2 over A2. Now, can't focus? Okay, thanks. So we're trying to figure out how much force is felt by the car if you apply only a very little force with F1. So let's solve this for F2. Again, we're trying to find out the force applied on the car to show that there's some mechanical advantage here to a hydraulic press. So solve for F2. God bless you. Solve for F2. What does F2 become? Over A1. Okay? Again, just multiply by A2. It's very easy. So here's what you can recognize. Here's what you can recognize. The force felt on the second object will be greater than the first force that you apply if this ratio of A2 to A1 is what? Again, let's pick a number for the force you apply. Give me a number for F1. 3 newtons of force.
If it's greater.
Okay, 3 newtons of force. Now, I want F2, I want the force felt by the car to be an advantage force, like more than 3. I apply 3 newtons, but I want it to lift a car. And a car might weigh like 2,000 newtons or some large number. How is that possible? If A2 over A1 is what?
Greater.
Then what?
The force is the other.
Then A1, then
If what?
A1. If the ratio is greater than A1 on top.
Close, but not right. You make a mistake in your wording.
The fraction.
A1 has to be smaller
What is it?
than a smaller value.
What does?
A1.
A1 needs to be a smaller value than A2 is what's important. The fraction itself needs to be greater than 1, not A1, but 1, okay? The fraction A2 over A1, if it's bigger than 1, doesn't it make this answer bigger than 3? If I multiply 3 by a number bigger than 1, what happens to it? It increases. If I multiply 3 by a number smaller than 1, what happens to it? Everybody? It decreases. This is arithmetic, like 5th grade, right? So, if I have a fraction that's bigger than 1 as a result of A2 over A1, I'll get a mechanical advantage. So for this to work, go back to your diagram. Yeah, so this A2, look at the area of A2. Isn't this area over here, if you just look at the diagram, I'll zoom in and make it easier. The A2 area is clearly bigger than A1. What am I hearing? Is that next door or is that really in here? It's got to be next door, right? What is that? Jesus. Okay. So A2 right here is bigger than, listen, A1. It's in the diagram, it's obvious, but mathematically we're showing it. So let's see that here mathematically. This ratio here needs to be greater than 1 for F2 to be greater than F1. Again, if you want the force felt by the object being lifted to be more than what you're applying, which is what you want, that's what hydraulic lift is all about. You apply a little force, you get a lot of force out of that. All you need to do is make sure that the area where the object is being lifted is much bigger than the area that you're pressing on. And that's it. So all you do is press on a small area, and as long as this is a big area, it lifts an object that's much heavier with very little force. Okay? Much less force than the other. Question about it. Okay? How much more will it be by? Will it be by whatever the ratio of A2 over A1 is? Look at the ratio of A2 to A1. Pick a number for A2. 7. Okay, let's make A2 7 hypothetically. And let's make A1 3.5. Shh. What's the ratio of 7 to 3.5? What is it? 2, not a half, but 2. 2 times 3 gives me 6. So since the ratio of the areas is 2, the second force will be double the force you apply. So if I apply 50 newtons, and that area is double this area, that'll feel 100 newtons. If I apply 60 newtons, that'll feel 120 newtons. So the ratio of the areas is what dictates the magnification of the force. So the mechanical advantage is really a function of the areas only. If I increase the area of the object being lifted, and the area I'm pushing on is very, very little, what I do as a result is I end up increasing the force felt on that object. Okay? A hydraulic press is a function of cross-sectional areas. Cross-sectional areas. I gave a bonus for this 1 year, but it's really complicated to actually create something like this at home. So I'm not going to give you a bonus for hydraulic lift here. But what you could do, if you got like an old school mercury pressure barometer, which measures pressure, and you push down the plunger on one end and a different cross-section on the other, you can notice the difference right away. Okay, you just need two different cross-sectional areas. But you need it to be a closed system with no pressure leaking out, so it needs to be sealed like a ceiling. So it's not an easy extra credit to do. Okay, but the concept is, again, the mechanical advantage that's important here.
In a series book, or I was like,
Okay? If you want to jot that down, you can. Mechanical advantage is the ratio, A is equal to the ratio of the areas.
yeah, I was kind of.
Let's look at the first example here. James, why don't you read it for us, please?
Hydraulic lift of 550 Newton force is exerted on a 1.5 meter square piston in order to support a weight that is placed on a 4 meter square piston. How much weight can the wide piston lift? How much pressure is exerted on each piston?
All right, so we've got a force applied to an area on one side. We've got the area on the other side, which is clearly bigger. So it's going to be able to lift a heavier object than 550 newtons. Again, just to visualize this, imagine I'm pushing with a certain force, but there's a bigger area on that end of the lift, that can feel force, that force felt to be greater than the force I pushed with. Look at the ratio of the areas. What's the ratio? What's the ratio of the areas?
4 over 1.5.
4 to 1.5, so 8 to 3, right? 8 to 3 if we do ratio, double them both. The ratio of areas is 8 to 3. Double 4 is 8, double 1.5 is 3. So the mechanical advantage here we're going to get is going to be really 2.66 times more we have. 8/3 as a fraction is 2.6 repeated. So that means that the force felt will be 8/3 times this 550. Well, let's prove it. Let's use our equation. It doesn't matter which one is which. Okay, if you call A1 the bigger or the smaller, it just reverses the ratio. It doesn't matter, you get the same answer, but you need to be consistent. For the sake of being consistent with the definition on the previous page, I'll call A2 the bigger area. I'm just going to default to that. Doesn't matter though. So we're trying to figure out the force it can lift. And then the second area is the smaller one. A1 is the smaller area, we'll call it, sorry. And the force applied is 550 newtons. Okay, so you apply 550 newtons to a small area, so the larger area should lift with more force. So we'll solve for F2. Plugging in numbers here, we're going to clearly see that we get 4 and 1.5, there's our ratio, times 550. So for those that were confused a minute ago when I said 8/3 of 550, that's what I'm saying. This is 8/3. 4 over 1.5 is 8/3. You're doing 8/3 of 550. 8/3 is 2.6 repeating. So you're multiplying 550 by a number greater than 1, thus you're increasing what F2 would be relative to what F1 would be. What do you get for F2?
1466.67.
1466.66.
Yeah, 0.67.
And that's a value of newtons. So the mechanical advantage in this problem, again, is 4 over 1.5, or 8/3. Okay, that's the mechanical advantage involved here. Think about how, amazing this is to conceive. What if you need to lift something that's extremely heavy? You have no way to lift it. You know, some people might use pulley systems, and pulley systems work. They work really well. Well, a hydraulic press is a very, very simple way to do this. And you'll hear the term, well, I'll leave it at that for now. Okay? All right, the second part of the problem says, what is the pressure felt? How do I find the pressure?
Equation.
Yeah, which one should I use? F1 over A1 or F2 over A2? F2 over A2?
Yeah.
Yeah? Anybody else?
No,
I want to find pressure. You just told me pressure is force over area. So should I use this to find the pressure? Or should I use this to find the pressure?
any of them,
Thank you. Why?
because they're both the same.
Guys, they're equal, aren't they? Look at the equation. Pascal's principle states that these are equal. So the pressure felt at any point in the fluid is the same, even the walls. So even though you're getting a bigger force out of it, the pressure is still the same. Because here you're doing what? 550 over 1.5. Here you'd be doing 1466.7 over 4. Either way, you get the same pressure. Because Pascal's principle tells us the pressure exerted throughout a fluid is the same. So this concept of finding the pressure on each piston, it doesn't matter. It's the same for both. So pick one or the other. I would personally pick what was given. I picked 550 over 1.5 because that number was given to me and it's easy to calculate. My 1466.7 works also, but in case I made a mistake and I want to get a right answer, I could kind of look at that again. But it doesn't really matter at this point. What do we get for the pressure? Okay? That's the pressure that is felt on either piston. It doesn't matter which one you check. Even the walls inside of the hydraulic press, the walls inside that cavity are feeling the same pressure. Everything inside that cavity is feeling this pressure. Okay? Everything is feeling this pressure. Now, if I remove the force though, and both pistons are no longer have any force on them, I'm not going to feel any pressure then, right? It's just going to be atmospheric pressure. That's all it's going to be. You're not going to have this extra pressure here. Remember, what is this pressure a measurement of? This is what's called, and I need to explain this word, maybe I'll explain in a minute, but I'll allude to it now, I guess. This is called gauge pressure. Jot this down, please. This is gauge pressure. The pressure that's felt inside of the hydraulic press, not including atmospheric pressure. This is not considering atmospheric pressure. Because atmospheric pressure pushes down on both pistons, so we don't need to consider it. It's like it balances out. It doesn't actually affect this. This is the pressure felt inside the container, not including the atmosphere.
If atmospheric pressure is felt on everything on Earth, will we ever have to account for it?
We do, yes.
In what situation?
We're going to see when we look at pressure as a depth underwater. We want to find out the overall pressure felt on a body or on an object under the water. Okay, we'll add it to the pressure felt on the water. Take the atmosphere, add the water, you get the overall, it's called absolute pressure of the body. Okay? Now, it's very useful if you're, like, if they're running cable along the ocean floor, like a lot of electrical cable runs across the ocean floor. A lot of, like, things, like if they want to send out robots down to certain depths, if they know the pressure is too much, what will happen to the robot? Yeah, it implode on itself. So they have to know these values of pressure, including the atmosphere.
Are there electric lines along Atlantic?
Like from Atlantic, from like the U.S. to
Yeah.
like Europe? I think there's like one or two that Verizon runs. They have some sort of networking lines that run through the world, yeah. I'm almost positive, because I read an article recently about the possibility of some private firms wanting to build transatlantic cables. But to do it like somehow as like a cable running over, it's sort of ridiculous. That wasn't feasible.
How do they get them done? Do they just drop them?
I don't think they're actually on the bottom floor. I think they're probably like a suspension cable that's going across the whole way. I don't know, maybe Google real quick, check for us, I'm not sure. No, these questions, guys, these are really interesting questions, but I don't know all these things, I really don't. If I knew it, I'd tell you for sure, but I'm interested when I hear these questions. Right now, this is the kind of person I am. I have 97 tabs open in my Google Chrome browser on my phone right now, I'm not joking. And all the tabs are like, I like to look at all these like different technology news feeds, and I open stuff, and sometimes it's like a 5-minute video explaining it, so I don't get a chance to look. So I've got like ridiculous things. Like one the other day was like a person, this guy took, you know the things that they put in like livestock to track them, so they don't lose livestock on farms, they put these little trackers. This guy tracked himself for like months at a time, injected himself with a tracker to see what it would look like, to see all this stuff, and did a whole experiment on it. Like that's one of the tabs I opened. I just find this stuff interesting. So this, what Johnny asked, that stuff interests me too. Yeah, I'm curious. I wonder if they actually do have something like that. I don't know. Yeah. There's a guy right now in China that apparently developed a generator that is more than 100% efficient, which is like unheard of. It's never been heard of. So a generator is like you put in energy to turn something and you get energy out, right? You put in mechanical energy and you get electrical energy out. But say I put in like 35 watts of power. All I'm going to get out is like 25 watts. There's always some loss of energy. This guy somehow is claiming to have done all these experiments with this generator he's created that uses electromagnets, like electromagnetism we've talked about with solenoids, and can generate more than 100% efficiency, which is like unheard of. How could you get more energy out of what you put in? The concept that Einstein came up with is that energy can either be created or destroyed, but only changed. So he's like almost creating new energy. So I was reading the article the other day, but it hasn't been verified by any sort of like scientific journals or engineers. People have to go to his facility to test it out. But it starts with like low end. He probably has to get like, you know, very like not reputable scientists to say it's true. And then people that actually have some, you know, status quo can go there and do it. And then if they say, oh, he's right, this is working, then it's valid. But the concept itself seems impossible. Anyway, that's a side note. Let's keep going. Johnny, if you find it, let me know. Cooper, same. If you find something, I'll then stop and we'll talk about it. All right, so let's talk about pressure varying with depth. It's actually really, really simple to understand this. And imagine you're underwater. Imagine you're underwater, and it's pitch black out. Okay? Now, imagine that below you there's a light in the pool. Focus, Jack. Come on. There's a light in the pool below you. The light shines upward. Okay, the light shines directly upward. The whole bottom floor is just LEDs, make it easier. The whole bottom floor of the pool is LEDs, so the light is shining upward. And if you're looking, imagine you're underwater. You're not above the water surface, you're underwater. And imagine you're in aerial view. The whole pool would look lit up, except for an area where it'd be a shadow of your body. Does that make sense? Yes. Imagine the whole bottom floor is lit up, and the light shines straight up. There would be a shadow above your body. The shadow above your body represents the channel or like a column of water. Imagine the water above, from your body to the shadow, the water between those. The weight of that water is the pressure that you're feeling.
The weight of the water on the shadow.
Okay? So the weight of that column of water, so let me demonstrate this for you. If you have, so here's the bottom of the ocean, or the bottom floor. You have this rectangular solid here. Okay? Now, the water level's up here. There's a rectangular column of water above this. Extend this, 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 and think about this as a column of water. Okay, this entire thing, that black rectangular solid, is like a channel of water above you. That channel of water is what applies pressure to the object above it. Again, is what applies pressure. And it turns out, this is crazy to think about it, that it's independent of the area of contact. So if I'm standing in the bottom of the water like this, and then standing like, or like laying like this, the area actually doesn't matter, which is weird. We're going to see how that cancels in the equation in a moment. Okay? So let's take a look. Let's start with our basic equation of pressure equals force over area. Now, the force felt by that channel of water is the weight of the water. What is the equation for weight? mg. So let's replace that with mass of the fluid times g. So again, all I'm doing right now is replacing F with mg, because F is the weight of the water. Okay, this is really what F is, Fg really. I'm replacing it with this formula right here. Now, the mass of the fluid let's say, is unknown. What can we replace mass with from what we've been learning in the previous section? Mass equals what? Anybody remember?
Density.
Times.
No, density times volume.
Good. Density times volume. So we have pressure equals force over area. If the force exerted is the weight of the water, the weight of the mass of the water rather can be replaced with density times volume. We've done this like 5 times now. You should know this by now. If you don't, the formula for density is mass over volume. Solve it for mass, you multiply by volume. This replaces mass always. Now, the volume of this rectangular solid, this is where it's going to get geometrical on you. Okay, the volume of this rectangular solid, and any rectangular solid, is the area of the base times the, anyone? Geometry. Height. Area of the base times the height. Okay, so yesterday, or 2 days ago, or rather Friday with you guys, we started off this topic of pressure as a function of depth, and we never finished it off. So we started by talking about the weight of the water on top of the column, or on top of the object, as a column of water. Now, the weight of that water is F, so that's mg. But m is really rho v. This is kind of where we left off at this point. We paused because the bell rang. And we're going to make some sort of a simplification now. Here's the simplification. And this is something that I'm explaining to you differently than I explained in the other class. I want to see which way I'll go better. Imagine if you were home and you took a bunch of coasters. What's a coaster? Yeah, you put your drink, all right? Okay. So imagine a coaster that's about this thick or has some thickness to it. And you stack like 50 coasters. You would get some sort of a cylinder out of it, assuming they were circular coasters. You would get a cylinder. If you had square coasters, you would get a rectangular prism. That's what we see right here. Take a look. This is a rectangular prism. The volume of any rectangular solid, assuming it's the same throughout, is the area of the base times the height. That's what I left you off with at the end of last class. The area of the base of the object times its height. The area of the base is shaded in black right there. Well, the area of that base is the same as the area of contact with the object. Look at the object in red. I'm going to highlight in blue now the area of the top of the object. Okay, I'm showing you in blue. That's the area of the top of the object. The black shaded region is the area at the bottom of the column of water. If volume of something is equal to area times height, I can replace the numerator right here with the area times the height. And what happens as a result? What happens as a result?
It becomes P plus G.
That's not a plus sign, that's an F.
Oh, sorry.
So what does it become?
P over. That's it. P G. Oh. PhD.
Yeah. PHG. It's rho. It's rho. Come on. So it's rho. Remember, guys, this is pressure out here. This is density in here. Density is called rho. So the A's cancel. That's what I'm trying to get at here. So you get rho Hg. Rho Hg. So what this tells you is that the pressure felt under the level of the surface of a fluid is a function of the density of the fluid. What does H really stand for in this scenario? The height of the fluid. What is that? What word do we use in boating and when we go out in water? What do we use? Depth. Think about it, right? You go into a pool where you say, how deep is the water? It's the depth. So H, yes, it's the height of the column of water. But if I scroll back up, the column of water is from here to here. That's called your depth, really. But the formula we're going to use is H, okay? So pressure is the density of the fluid times gravity times H. This is called, write this down, gauge pressure.
Okay, so, I'm sorry, that one is actually a P, not the symbol that's.
Again, that's the symbol rho down here,
But the first one is.
and the first one is P for pressure. So pressure equals rho GH. Pressure equals rho GH.
If we do this
Now-
now,
What is the units of pressure?
Pascal.
Pascals.
Row.
For rho, it's density, so it's kilogram per meter cubed.
Oh, right.
Because the density formula is mass over volume. What is gauge pressure? Anybody do ever any instrumentation or any work at home on stuff? What does gauge pressure mean? You know what it means? Yeah, in the container. So if you talk about the gauge pressure in a tire, you're talking about the pressure inside of the tire. Now, think back to last class on Friday. We talked about the fact that there's always something weighing you down. What do we call that? Atmospheric. Gravity pulls you down, yes. But there's something always weighing you down. Atmospheric pressure from the air above you. So when you're underwater, this is the pressure increase that you feel. But the actual pressure you feel underwater is called the absolute pressure. And the absolute pressure is equal to the atmospheric pressure plus the gauge pressure. And that makes sense. Think about it. You add them together. If I was standing on top of a box, and then somebody, say, my little cousin jumped on my shoulders, my weight would increase, the force on the box would increase. It would be the sum of those weights. So here, if the pressure underwater is given by gauge pressure, and the atmosphere is also pushing down on the water, the absolute, meaning the overall pressure you feel, is the atmosphere plus the gauge pressure. So you will sometimes see a formula written like this, and I think this is how I wrote it on your formula sheet at the bottom. I think I wrote this, P0, that stands for atmospheric, plus rho GH. I'll read it again so you know clearly. This is P. This P by itself out here, you should know means absolute because there's a plus P0 here. Again, if I saw this formula up top, I would know it's gauge pressure. I know right away because there's no atmospheric pressure being added in the front. The minute you have the same formula from gauge pressure plus P0, where P0 is given to you, it'll be on the formula sheet or in the problem, atmospheric pressure, you add these two together, you get the absolute pressure felt by the object under the fluid.
Why is it zero?
Zero, it's really called naught, P naught. It means the baseline pressure. Whenever you hear remember earlier this year, guys, we did VF equals VI plus AT? Later in physics, you'll hear VF equals V naught plus AT. Naught, I means initial. This is the starting pressure from the atmosphere plus the pressure from the fluid that you're actually submerged in. You always have this pressure on you if you're on Earth. So it's your starting value, not being the starting. Okay, like a PI.
So it's a constant?
It's a constant. Okay, and again, I gave you that constant earlier, but in case you're wondering, this constant is 1 times 10 to the 5th pascals. And then whatever else goes here. I don't know. It depends on the problem, obviously. Okay, but this constant is either given in the problem or on your formula sheet. Somebody check your formula sheet, check if it's there. If it's not, then it means I put it in the problem in the test.
It is.
It is.
Nice.
What did I write it as? 1 times 10 to the 5th, or did I write it as 1 on 1
You
point
wrote, you wrote 1 ATM equals, PO equals 1 ATM equals 1 times 10 to the 5th.
Perfect. Okay? So you're going to see that on your formula sheet. So the idea again, and last year the classes really confused us, so I want to make sure we're clear. This is a very easy problem. It really is. It's not a difficult problem. But a lot of people completely ignore this P0 concept. If you're underwater, the gauge pressure, the pressure felt in the container, in the water, is just rho GH. But if you're trying to find the overall pressure you feel, it's the water pushing down at you plus the atmosphere. So you have to use what's called absolute pressure, P0 plus rho GH. So depending upon the problem, you either use simply rho GH or P0 plus rho GH. All right, 3. Let's Go ahead and read it for us. Go ahead and read it for us. Mullen, go for it.
Calculate the depth in the ocean at which the pressure is 3 times atmospheric pressure. The density of seawater is 1,025.
So how far down in the water do we have to go for the pressure we feel to be triple atmospheric pressure? Right, that's the real question. How far do we have to go? 3 feet? A lot more than 3.
That's a simple question.
No. We need a little more math to do this one.
3 times.
We're tripling the atmospheric pressure, but that doesn't directly relate to the distance. So let's take a look at this. We are looking for depth. Depth. What variable is depth in this case? H. Start by writing that, please. Rho GH. H stands for depth. Next.
Yeah.
We want the actual pressure to be triple atmospheric. So I'm going to write this out. Tell me if that makes sense to you. Pressure equals triple atmospheric. Atmospheric being P0. P0 is a number. I'm not going to put that number in, and you'll see why in a moment. Okay, don't put that number in yet for P0. But that's what the pressure needs to be. Triple times 1 times 10 to the 5th. The density of the fluid, and notice I always put subscripts for density. Why do you think I do that?
Because the P's and the symbol can look like.
Yes, the P and the rho look similar. So whenever I use rho, I put the subscript of F or 0 to indicate a fluid density or an object's density. To know that I'm talking about density and not pressure there. The density of salt water is just above regular water. Regular water is 1,000 kilograms per cubic meter. Salt water is taking salt and adding it to water, so it's got to be more dense. Now, at this point in time, we know the density, we're looking for the depth, we know what the pressure should be. Let's use the formula for absolute pressure. It does not say a thing about gauge pressure here. So we, by default, are going to use atmospheric pressure, or absolute pressure. There's our formula at the bottom. What should we replace capital P on the left-hand side with? 3 times PO. Do you see why I'm not putting PO in now, by the way, the number? I don't pick up on it yet? Why didn't I put a number in for PO yet? I'm going to be able to, not cancel, what's the right word? Not substitute, almost substitute, but not, that's not the right word for it still.
Subtract.
Yeah, combine or subtract, combine like terms. If you use the word cancel, it's like you cannot cancel these. They don't cancel, but you can combine like terms. So let's replace P with 3P0. That's like having 3x and x, right? That's what I'm seeing right now.
But did you say we're not using gauge pressure?
Correct. And gauge pressure would be this formula on the top right that I'm going to cross out so you don't confuse it. That's gauge pressure. We are not using that formula right now.
But you're putting that in
No, remember, this is the absolute pressure.
for, right?
Absolute equals atmospheric plus gauge.
But you're not using just gauge.
Correct. We're not solving for the pressure felt from the water. We're trying to find out when the overall pressure felt is triple atmospheric. So the combination of pressure from the atmosphere and gauge. We know rho. Rho in this case is 1025. We know G. And we're trying to find H. So at this point, if you want to plug in numbers, you can for P0, but I would subtract P0 from both sides first.
You can just subtract even those being multiplied by 3.
How come? How do I know I can do that? It's not attached to anything else. Look, this is like, ready? 3x equals x plus 7. Wouldn't you move the x over and combine like terms?
I would divide them.
Not if you have a plus 7 on the end, you can't. Right? If I have 3x and x, I have to subtract x over. 3x minus x gives me 2x. Okay, always combine like terms before you can divide anything. So H turns out to be 2P0 over the product of rho and G. Okay, H is equal to 2P0 over the product of rho G. P0 is a constant in your book, in your formula sheet and your book both. Just plug it in. 1 times 10 to the 5th. I got 19.9. Check your parentheses around your denominator, remember?
Wait, you give us.
Hey, 4 people on this test, 4 of you I counted because I was thinking about it because we talked about this, forgot a big parentheses around their bottom. Better than the previous test. Okay, it's usually a lot more, but again guys, you need parentheses around this denominator.
Did you give us PO?
PO is on the formula sheet. It's given as 1 times 10 to the 5th pascals. It's the pressure of an atmosphere weighing down on you. Okay, so again, 20 meters, that's about 60 or so feet. The pressure you feel outside has been now tripled. Think about that for a second, seriously. The pressure you feel now is very little. You don't feel any pressure. But by the time you get down almost 60 feet, that pressure is already tripled just in the water. So think about deep sea divers that are going down a lot further than something like 60 feet. That's not very far. There's a lot more pressure felt as you go much further down in the water. And those are clearly directly related, right? As you go deeper in the water, more pressure is felt by the object. Mm-hmm.
For 1 times 10 to the 15th, can you just say 10 to the 15th?
You could just put 10 to the 5th, yeah, absolutely. So you could write it as 2 times 10 to the 5th because there's a 2 in front there.
It wouldn't be negative because we can only go down.
Technically, yeah, the distance is negative, but I'm asking for a depth, so I assume you're talking about down anyway. Yeah. Either way is fine to give an answer there. Listen carefully. You're not going to have homework for the lab, which is good. The lab we're going to do in the second period is one that's done in class. The next lab you will have homework for, okay? Or you have some more work to do. This homework and 9.3 I'm going to have due tomorrow. Okay? It's a lot, I know. I'm going to probably give you time at the end of next period to work on this stuff. The lab that you're going to do in the next period is not going to take the full period, and the notes we're about to do are very quick. The notes we're about to go through are real simple, mainly conceptual. We've done almost all the math from chapter 9 at this point. Okay, we've done the math with buoyancy, right? Buoyancy equals rho vg. And now we're looking at the math with pressure. Pressure equals force over area, or rho 0 plus, P0 plus rho gh.
Would you want the homework all in one document or?
Yeah.
9.2 and 9.3 should be separate. Okay?